So today we're going to talk about static and dynamic libraries and how they are implemented. We'll start with static libraries, which are conceptually very simple, but not so frequently used today. Then we will go and discuss how dynamic libraries are built, and specifically one technology which is needed for implementing dynamic libraries is position-independent code, and it will get a little bit involved. And then we'll end by essentially looking over how real programs get launched or started on the Linux operating system. And that will finish our two-lecture set on essentially internals of processes and organization of linking and loading. So let's start with static libraries first, which have .a extension on the Unix systems. So conceptually, a static library is just a collection of object files. So it is as simple as that. It's really just someone bundles object files together with an archiver. So in Unix systems use a specific archive format. There is an R tool, which of course, like not many people use today, but this is specifically a tool which allows you to archive multiple object files together, right? So it can conceptually support collections of any objects, but today it's normally not used for anything besides static libraries, right? So for example, how do you create a static library? So, well, you're a developer who develops a library, right? So for example, you're a developer of a libc library, right? And you use your compiler for each C file, because you will use something like a make file and a make tool to essentially compile those files automatically, right? But like in the end, the compiler is invoked on each file individually, right? So this C file will be like used with -c flag, means compile but do not link, to produce an object file, right? Same with printf, gcc, produce printf object file, random.c, produce random.o file. And then we use an AR tool, which essentially just takes all these object files and packages them as a single archive, which essentially we see as a libc.a, a static library, right? So here's a couple of examples. So you can, for example, do it yourself. So you can say, oh, sure, like let's use AR tool, take a bunch of object files and essentially just create a static library collecting those object files together. And both Unix linkers and compilers can read those libraries, right? So for example, you can invoke GCC compiler saying, okay, I will take my C file and link it against the lib class.a object static library, right? And for example, if you put the library on one of the standard paths in your system, something like user local lib, right? So you can invoke it with -l flag, meaning that the compiler will go ahead and will take this and will, in that file, will search for something like lib class.a, right? So you probably, people who were programming Unix machines or Unix systems, they were using this -l flags to link against static libraries. And if you want to invoke a linker, you do something like that. LD as a linker, take your main.o file, pass static library as an argument. And it's equivalent to essentially just invoking GCC on all these object files individually, because the static library is nothing special, nothing besides a collection of object files, right? So that's conceptually simple. And of course, when the linking happens, yeah, so what happens is that you like remember this general story that if your main file, like main.o, which was produced from main C, was using printf, right? When you compiled it, printf will be marked as undefined, right? And so it has to be provided by one of those like printf.o files, right? So here's a printf, and in this o file, this like it will be marked as defined, right? And so essentially the linker should go through all the object files and collect all the defined and undefined symbols, and then essentially eventually when it does the linking, like resolve all the unresolved names, right? And sometimes to improve the speed, right? So the search, some kind of an index is added to this archive, right? So that which linker understands, and it can like essentially quickly figure out where the specific symbols are located. Okay, so shared static libraries are conceptually very, very simple, but and what's the benefit of a shared library? The benefit is roughly speaking, one developer or a group of developers, like some people who do the libc, well, handle the libc project, right? And it's a complicated project with tons of C files and whatnot, right? And then they provide it to you as a static library, right? So libc.a, right? And so what, you don't have to handle the compilation step here. You just simply link against this library. And while link and run, essentially, you can essentially like pick up all the symbols. And if they don't have any external undefined symbols, then you're ready to go, right? And also, obviously, but that's essentially, that's just a part of the story, right? Because what you want to really do, you want to somehow share the libraries between programs, right? Meaning that, imagine the following story. So here's a bit of motivation for you. Imagine we have a Unix system, and a typical Unix system has roughly, let's say, 1,000 programs, right? And each of this program will have a copy of printf, because it's hard to imagine a program which never does a printf, right? Never outputs anything on the screen, or unless it's like a C++ program, like all C programs will definitely output something, and most likely will use a printf function, right? So you will have 1,000 copies of printf, right? So roughly speaking, you have 1,000 programs, right? And each of them will have a printf. So how big is printf, you think? Well, it's a good question, but printf is a complicated function, because remember, it handles conversions from into like, you can convert some numbers to strings, you convert some floating points or doubles to strings as well, right? And all this logic has to be implemented. So it gets reasonably large. So for example, specifically on my machine, which I'm running or used to run a couple of years ago when I did this test, I have 2,500 programs in user bin folder, right? So I ran ls and piped it to wc-l, right? And printf is a large function, like we agreed, so it might like require 5 to 10 kilobytes of code, right, to handle all the conversion corner cases. I mean, I made up this number, so I don't know for sure, so you're welcome to essentially look at printf and somehow figure out what the size is, but let's assume. So, but if you multiply these two numbers, you get that if you put printf in every program which I have in my system, right, I will easily waste 10 to 25 megabytes of disk space, right, just for printf, because, well, I have program A and it has a printf, like this is printf here, like this 10 kilobytes, right? It's my, I don't know, maybe it's my tiny hello world program, right? It's on disk somewhere, right? And I have another program. Well, if I link all the programs statically, right? So like I was doing in a previous like sets of slides, right? So this is my, some other like hello, maybe it's your homework number 1, for example, or it's again like, well, has printf, and you have easily just 10 to 25 megabytes of space. And today, well, seems nothing, right? Who cares about 25 megabytes of space, of disk space? Because we're running like multi-terabyte disk, but like, you know, like even 15, 20 years ago, that was a significant amount of disk space, right? And also there's another thing. Okay, imagine now you load all these programs in memory, right? So for example, again, on my machine, if I do ps minus aux, so meaning that all programs show me the users, right, and pipe it into wc-l, I will see roughly 250 programs running on my Linux laptop. So it means that it's 1 to 2.5 megabytes of RAM, right? Again, today we have, you know, easily like 8 to 32 GBs of RAM seems like nothing, but it was a huge number 15, 20 years ago, right? So that's why back then these technologies were created and still are used today, right? So what it means is that sure, like you say, absolutely. My first laptop probably had like maybe 8 megabytes of DRAM, right? So it would like, I would sacrifice like a quarter of it easily to run printf, right? And keep printf in memory. So people were looking for an idea, so which would allow them to do the following trick, right? So I don't know if I have an extra slide, right? So I have it here. So for example, if you run program 1, which is like, let's assume it's hello world, right? So it's a program hello world. It uses some main function here, which might be reasonably tiny. And then it says, okay, look, sure, I will have this printf library linked in it, right? And then I will have another program. Well, as I was saying, P2, it also has like a slightly different main function, maybe even like slightly larger. Well, maybe it does a little bit more work, right? And would say, well, why not to like essentially have the copy of a printf in memory? But somehow, if those virtual memories, right, for two programs, we somehow can figure out a trick to make sure that in physical memory, we keep just one copy of printf like that, right? So it's like, and it's, we will like talk a lot about virtual memories and how they are implemented, right? So, but essentially there is a trick with page tables, which allow us to essentially map this memory twice, right? Here and here, right? Then you say, sure, I just, in physical memory, I just spent like really like this 10 kilobytes just once, right? And then in every new program, I start a new program, I will just map it there, right? Map a printf, and then the program can essentially just, well, call functions of printf, right? So, and that would be called a mechanism of a shared library. Right, this is a powerful mechanism because look, first of all, we have one copy of libc.so shared object, right, on disk, right? So we just only keep it once on disk. My main program, like is program 1 and program 2, they will be also on disk, right? So but they only contain their own, like these main sections, right? So this A will be here and B will be here. And the moment we will be starting the program, right? Let me change the color here to explain the story a little bit better. So let's do blue, for example, again. So the moment we create a program, we essentially dynamically link. So essentially we take this part of the program, take libc from disk if it's the first time, but maybe it's already in memory, right? So maybe one program was already started and this libc was already mapped there, right? We just essentially just map it again in this new program and use it here. So it's the beauty of it is that this one physical memory, it's a little bit hard to understand because I have to bring up these concepts of virtual and physical memory, which are totally unclear now, right? But roughly speaking, you say, well, I dynamically, when the program is loaded in memory, I somehow say, well, if I'm using printf, I will just be jumping here. I will just patch this address, remember, like some kind of a linking step. Essentially, I will find undefined symbols and essentially redirect them to these shared libraries, which will be mapped from physical memory, which is potentially already is in memory and used by other programs, right? So that's kind of a good story, right? So you say, well, that seems to be very, very flexible, right? Why not? Like, this is great. So we'll keep one copy on disk, one copy in memory, save a bunch of resources. And I mean, like I was saying that, okay, like copy of printf is nothing, right? But believe me or not, but those modern programs depend on tons of libraries, like what not, like, I don't know, like you often run again something like boost and what only we don't include, right? Even a simple program which does something with the network or disks, or implement some like key value stores which are linked from like external implementations and stuff. Well, yeah, we use a lot. So this like significant amount of resources can be actually saved here. Okay, but there is a couple of problems here, right? Here, let me just again continue with my motivation story. change to back to red. So this test is again like done a couple of years ago, Ubuntu 16.04. If I link my program hello int, which I was using last time in the examples, I say, well, link it statically, essentially, like do not allow any dynamic or shared libraries output the test program. It's only 725 kilobytes in size, right? So it's still like a little bit bigger because you say, wow, what is there? Like hello int, like it really just was adding two numbers. How come it like comes up to 725 kilobytes? Well, we'll take a little bit, but we'll look a little bit today that there is a bunch of stuff running before main even link. So like this libc, and it gets linked because, you know, like even to implement printf, you have to go through libc, which executes system calls and stuff like that, right? So, but if you say, well, sure, if we do link dynamically, so essentially, if you delete the static keyword, do the same, the program is only 7 kilobytes of RAM, right? So meaning that all this libc business, so essentially like all this, roughly speaking, 718 kilobytes are all loaded as shared libraries, right? And that's kind of like significant savings on disk, right? Because again, like if you do a find through your file system looking for all executable or files, right, you will find a lot, right? So the question is like how to build this idea. How can we share code in memory, right? There is this problem that the code section of the library, first of all, it has to be mapped read-only because obviously, right, well, programs cannot modify it because one program would override libc, right, and cross all programs in the system. But they also can they be loaded at different addresses? Here, let me try to explain, right? So imagine this is my program A. It has this main part unique to this program P1. Here's this to program 2, right? Right. If we say, well, we mapped, because maybe this space was used by some other libraries already, we mapped libc here. This is libc in one program. Remember, libc, in order to access its data section, so imagine there's like a data section for libc here. We have to relocate the code, right? So we have to essentially patch here all the references to global variables, right? Saying, okay, well, sure, like, by the way, in order to use libc at this specific starting at this specific address and data section starting at this address, well, yeah, we do relocate every time we have to move libc, right? So if, for example, here a little bit less space was used, right? And libc is mapped not at address A, but at address B here, right? Well, it has supposedly the same data section, right? And we again trying to access the same variable here. So maybe it's some global variable, let's assume G, like this G is now here, right? So these two addresses here and here, they have to be different, right? Because, well, G, I mean, like these two move instructions, right? Remember, imagine in each of this program, you have some move instruction which loads G into, for example, EAX. For example, you use like, wow, you use VX, right? For example, VX is like, no, you like literally use the address of G, right? But this address, like, well, we like when we link and load and relocate libc to run at specific address A, we write this address, right? And currently, while we say in the second program, well, this address is different because this G is at a different address. So this like one address might be X 1055, but another might be like X, I don't know. What's the good address? Like, let's say 755, for example, right? Here's the problem, right? So at this point, the question is the problem is the following. So the code of this libc, right? Suddenly this one and this one are not equal, right? So the code has to be identical to be shared, right? Because it's mapped once in physical memory, right? So if this program is in physical memory, we can't have two copies of this address, right? So because it's one memory, it has to contain one value. So what can we do? Well, one solution is to say, well, libc, for example, always starts at one address, like it will always start at A. No matter what happens in a second program, it also has to start from the same address A, right? And it's totally kind of a meaningful design decision, at least initially, right? Because you say, well, that fixes the problem, right? So if libc starts here, then my address here and here will be identical because my data section will be in the same place. Of course, data sections are different, right, in each program. Sorry, I forgot to say that because obviously they are writable. So in program 1, the data section will be in one physical memory, and in program 2, the data section will be in some other physical memory, right? But this large code section, right, or text section, right, has to be the same, right? It's read-only, no one can write into it, and it's identical, right? So it will always be relocated to point to the same address of the data section. And here, each program, P1 will have its own copy of data, P2 will have its own copy of data as well, right? So fine, works, right? But however, the problem is the following. So it's very hard to pick a unique address for each library. Imagine, well, you have libc, but then libc version number 2, libc version number 3, and it creates something like a DLL kind of hell, right? Because I think Windows was doing that for a while. So Windows was picking unique addresses for each library, right? And then for as long as you're lucky and this address is available in your address space, well, you get the possibility of loading a shared library. If this address is somehow already occupied just because, well, something happened, another library just grew in size and already took that address which was previously allocated to you, then you had to load a private version of the same shared library, right? So you lose gradually was losing ability to share shared libraries across all programs. And this is where this idea of position-independent code comes into place. So position-independent code is the idea that you can then generate code section of these libraries in such a manner that they can work at any address in your code. So essentially, you take this code of libc, you have a data section attached to it, but you can move it left or right in the address space without any changes to the libc code section, and it will just work. That's kind of amazing because remember, these move addresses are normally, they use move instructions, they use real addresses. So how does it work when you move it up and down? Because data section moves up and down. So this address clearly has to change. Well, do you have a guess how you can generate code which works irrespective of where you are in the address space? So, okay, so this is an important concept, the position-independent code, idea that you can generate code like that. So the main idea, I described it, generate the code in such a way that it can work no matter where it is located in the address space, right? Move it here or here, it works. Well, first of all, let's try to understand what needs to be changed in this code section, right? Because we have a pretty good idea about what is there in the data section, right? So, because what is there in the code section? We looked at the code, we know that how functions are organized, we understand the calling conventions, we understand the local and global variables and even heap variables to some degree, right? The question is, what needs to be changed, right? So first of all, what can stay untouched? Remember, local jumps are relative and local calls are relative. So if your function foo calls another function bar, which is defined right here, right, in the same file, that's a relative call because there is just some delta, right? Same if you jump to some label like L1 here, it's also a relative jump. I just say, okay, jump plus some number of bytes, right, from this current location. So this code can go up and down in memory with no changes, right? that's a good advantage, right? So you mean that nothing needs to be changed here. Also, stack data is relative to the stack, right? Because like, well, sure, like it's all relative to this ESP and EBP registers, which we're using to address local variables in a stack, right? It's fine. If we're moving this, if we're moving the code section here up and down, right? The stack can be anywhere. It doesn't really matter, right? We don't move the stack, right? So that's also a plus, right? So like already like local jumps, local calls, and stack doesn't have to be changed, do not have to be changed, right? That's great. So what needs to be modified, right? That's the question. So remember global variables, right? Because if they're in a data section, let's draw the data section somewhere here, right? If you refer to a global variable, you will use its address here, and this address is an absolute address somewhere in the data section, meaning that it cannot be delta. There is no instruction on x86 32-bit machine, which allows you to do a relative address here, right? So these instructions, like these moves, they have to be modified, right? And obviously imported functions, because if you have something like call printf, and call printf is in some other shared library, right, which also can get moved right up and down. And if your printf was originally leading you here, but this library gets moved, well, you have to somehow change this address as well, right? Okay, let's take a closer look at what needs to be done. Again, so this is just an example. So what are we doing here? So we are referencing a data section here in our main program, right? So essentially here is from last time. Remember we had this example where A was passing a string, right? And string was a global, I forgot what it was exactly, but something like hello world. It was obviously allocated in a data section, right? And so right now, this address is essentially, like roughly speaking, which would push on a stack here, right? It has to be changed, right? Because the code and data section can be moved around, right? So this address will be changing, right? So right now, if I understand, in this example, it's linked to that the data section starts at 0, right? And then it's like 16 bytes into the data section, something like that. Okay. Local function invocations. So A is defined here. Remember, this is just a delta to call A. So this like +3, because again, if you add bytes properly, you will understand that it's only 3 bytes away. No need to relocate, that's good. So the question is, how can we build position-independent code? Well, it's nice to ask this question live because it usually results in a nice discussion, but of course I can't. So let me just give you a hint here. So the main idea is that we add an additional layer of indirection for all references, right? So instead of just referring variables in a global variables in a data section or importing functions, we'll go through some tables. So instead of like doing a move of some variable, we say, well, let's do a move, but pick up this address from a specific table. And this table will actually contain the address of where the data section ended up being in memory, right? And the linker, when it like essentially loads us and like moves us up and down, will just update this table, right? Table of references. But if we can figure out how to essentially put a distance here between the code and this table, and if we say that this distance never changes, then it will be golden, right? Because if this distance d is always constant, like we move these two sections like code and this table together up and down, distance stays constant. Well, if we can address into the table using this constant distance, the code doesn't have to be changed. Nothing has to be changed here, right? Okay. And well, that's essentially the trick, right? So the distance between the code and data section where this table is located remains constant, even if the code is relocated. So, right? So this is our code. This is a data section. This is this table which we're talking about, right? It contains pointers to data section. But this distance to this table is always the same. From here, from this location in code, from here, from this location in code, it's like a different distance. But even if you move the whole thing up and down, right, in the address space, it doesn't change. Both this delta 1 and delta 2, they stay the same, right? Because, well, it's the same, like they're moving together. Okay, so this is what we'll be doing. So we say, sure, that's my move instruction, which tries to address a global variable, right? This is like code section, right? And the distance here is like from these low addresses to these high addresses is always the same. This is the distance, right? And if those bits, high bits change, meaning that we move it up and or down, all the low bits don't change, right? Well, I hope it's more or less intuitive at this point. And of course, this level of interaction, instead of referring to the data section directly, which would require relocation here, we just like say, well, let's load a value from here, and it will be a pointer. It will contain a pointer to the bar, this first variable, right? And every time we load it in memory and like moved up and down, each process will have its private, it's called global offset table, right? The linker will patch this addresses, this one, this one, and this one, that will be correctly pointed in your data section. But this code section is constant in process P1, P2, and so on. It doesn't need to be changed, right? It always remains the same. And it can be shared, read only across all programs, right? Okay, let's see how can we do this. Right, so it's just the same explanation. So GOT is patched by the linker at relocation time when the program is loaded from disk to memory, getting ready to run, right? And similarly, I mean, obviously, this is like if it's a code of libc, right, which we load from libcso, like, of course, like, sure, there will be a main program there, right? And we essentially, main will also have its own GOT, right? And this GOT might be pointing to, for example, like a printf, so which might be somewhere here. And the printf itself might be using some global variables, right? So it will be using this GOT to go through the GOT and access it, right? But this specifically can be shared between process P1, P2, and P3, for example, or how many processes you have in the system. Okay, here's the question: how to find the position of the code in memory at runtime? So first of all, why do we need it, right? The question is there an instruction which does this? Give me my current address of, like, if I'm like running this move instruction at some address, can you give me the address of this move, right? Because, well, why do I need it? If I know this address, imagine it's like X155, currently running at 155. The compiler knows the distance from this move instruction to the GOT. Let's assume it's like 3000, right? X3000. Then in order to access GOT, you just simply say, well, sure, if I know this current address, I will do X1055 plus 3000, right? And I can use it in a move instruction, because if I say, well, load me something from this address, X1000, like, let's put it like as 4055, right? You will load this address, right? So the moment you can find this and the compiler knows this delta, right? You're good to go. The question is like, can you find this address, the current address of you currently, like where you currently running, right? And this move instruction can go up and down in different address spaces, right? So all move instructions require absolute addresses on x86 32-bit machines, right? So no relative addresses, like you can't say move relative to EAP. That's not allowed. So by the way, 64-bit machines, 64-bit machines understood that this is a limitation, and now there is a EAP instruction pointer relative addressing, right? So which allows to implement position independent code a little bit more efficiently, right? But there is no instruction which allows you to learn the value of the current instruction pointer on 32-bit machines. So can you come up with a trick to do that? It's actually quite cute, right? So let me show you. Simple trick, one of the simple tricks. You can do a couple, right? So for example, if you call the next instruction, meaning that, well, call label 2, the compiler will generate the code which will call this instruction, right? So your instruction pointer will change from call from here to exactly here. But what will you get on the stack? Remember, the call instruction puts the address of the next instruction on the stack, right? So right here on very top of your stack, you will have exactly this address A, which you're trying to find out, right? You know the A because it got pushed as part of the call invocation. Well, you don't have to return for the count function, right? Well, you can simply like pop this address into EBX, right? Then EBX will contain A, and you figure out your address, right? That's one trick. Why not? It's kind of interesting, right? So you calling, you never return. Well, no one told us that you call instruction should always have a return. Call instruction is just a machine instruction. It will always do whatever it has to do, right? The CPU will just execute it, push a return address on the stack. And well, you don't have to return, you can just pop it into a register. And this way, you essentially, this A is the value of the instruction pointer which you're currently executing, right? Okay, that's interesting. That gives us a chance to build this position independent code. So here, for example, we say, well, let's call the next instruction. We'll figure out the EAP at this position. Sorry. We pop it into the EBX register, well, and at the distance, right? So for example, if this is happening right here, and your distance is this FFF, right? That will give you, like at this point, EBX will contain the address beginning of the GOT. And then you can like pick up a specific entry, maybe entry number 5 from GOT, right? Because you're trying to access fifth variable, right? Okay, let me give you a couple of concrete examples because, I mean, I understand that it's a little bit like, too much low-level assembly code, but hopefully looking at examples, it will help. So here we have a simple function, func, which uses this global variable, right? So let's take a look how the code is organized. And I'm using like more or less concrete examples. So you will see that when you launch the debugger, you will see those symbols like get PC thunk. So this thunk is this tiny little function here, which will help you to recover instruction pointer, similar to how you were trying to like, to how we were trying to do that in the previous slide. So here what we do is that, well, our goal is to access my global variable, right? We don't know where it is in memory because it's global, right? So it can be moved up and down. So first we call this thunk function, right? Which will land us right here, right? So essentially, this is what we have here. Well, in this trick specifically, what's on top of the stack, by the way? On top of the stack right now is obviously a return address, right? Which is the address of this instruction. This is this address, like 444, right? So we're moving it from this stack into ECX register and immediately return. We're kind of breaking the calling convention here, but compiler is smart enough to understand it, meaning that ECX will contain the current instruction pointer, right? That's cute. So we save EAP into ECX, very similar to the trick in the previous slide, slightly different. Now we add the offset because the compiler knows that this instruction is like 1000 BB0 bytes away from the global offset table. So we add it into the ECX, right? And at this point, we can access address of a specific GOT entry, like access address of the my global, right? So my global is not like immediately at the beginning of ECX, right? So here, that's where your ECX is pointing, right? And this is 0 address. So you're subtracting 16. So maybe there are like 2 more entries here, right? So we're looking at this pointer. Right now it will be in the ECX register, right? So we loaded the memory. We loaded the memory from this address, right, into the EAX, right? And if on this next slide, the actual value of the variable, which is pointed by the EAX, is loaded in the EAX register, right? So this EAX will get the value of my global after this instruction, right? Okay, cool. That's what we wanted. So we got the my global, and we do this addition after that. So like our A and B are arguments to the function, so they are on the stack available relative to EBP according to our calling convention, right? So we first add A, then add B to the EAX, and then, well, exit the function. Remember, EAX contains the return value, so it will be returned from this function. Agree? So that was interesting, right? So clear. What about function calls, right? So meaning that, imagine again, this is your main function, right? And users call printf. You say, wow, but I don't know where this printf will be because my libc library can be anywhere, right? It can be loaded at address 1055, or can be loaded at completely different address, something like x16055, right? And you don't really know, right? So what can you do? You can probably do the same trick, right? You can say, wow, GOT, first of all, like, let's essentially go here and pick up the address of printf and go here, right? And this trick would work, totally. This trick works, like, don't be surprised. There is one real problem, that the number of global variables is relatively small. Like how often you use global variables? You don't use them. Like, it's like computer science 101, never use global variables, right? But the number of functions is huge. So this GOT for functions is large. And it's why the trick will work. In practice, only a small subset of those functions is used in practice. Like you might call printf and a handful of other functions, but there are hundreds of functions in the libc library. Most of them are not called. So the problem is that every time you load your program in memory, you have to construct correct GOT for all of these functions, right? All of them, like for hundreds of them. And it takes time. And when you do static linking, it's fine because, like, why not? Like, you do that statically at compile time. No one cares. Like, it will take you a little bit longer to compile. But when you start the programs, people want to do exec very, very fast because maybe you're forking like and executing new programs to process some incoming requests, for example, right? So, and this linking, like resolving all the symbols would take time. And what is done instead of like resolving them eagerly, they are resolved lazily, meaning that only functions which get called will get resolved. Everything else will still be pointing to nowhere. Let me show you how it works. So it's called late binding. When a shared library refers to some function, the real address of that function is not known until load time. Resolving this address is called binding, right? And as I was saying, libc has over 600 functions, right? The number of functions is much larger than the number of global variables. That's what I was just told you, right? And it's okay to bind all routines, right? When the program is statically linked, because it's done offline. But dynamic linking, you say lazy approach, do not bind them because it takes too much time, but only link them when they're used, right? And another technique is used for that, for this lazy binding. It's using a data structure which is called procedure linkage table. It's conceptually very similar to PLT, so again, to GOT, global offset table. So when you call a function here, right, in this slide, you call a function, it will, well, land you on an entry. There will be a label here, right, like a specific address, right, and it's a relative delta, so it's always a relative call, so you can move it up and down, it's no problem, right? What you do instead is that then you say, wow, what if I jump to the entry in the global descriptor table, or rather not to the entry, but to the address contained here. So here is an address. So I will jump to this address. And the first time you jump, this address is always pointing back. So essentially you say, wow, I'm about to call a function for the first time. So first of all, I will prepare some arguments to this function which will do a resolution of this symbol or binding, and then jump to typically it's PLT0 and call this resolver, right? Resolver does something, figures out where this function is located, and what do you think it will do? It will patch this address. So instead of the second time you execute this, instead of jumping back here, you will jump directly to the function, right? Which is located somewhere. So essentially, first time you jump back, do the resolution, and the second time you jump immediately to this function here, right? Okay. So that doesn't seem super hard, right? So it's just the same kind of tricks with GOT, right? But this is one step further. Let me explain how it works. Okay, there is like a lot of text. Let's try getting through that. So, okay, first of all, PLT is part of the executable text section, right? It's a set of entries, as I was saying. It's labels, like label 1, label 2. For each function, you will like external function, which is not yet resolved, right? 1 for each external function. Each PLT entry is a short chunk of executable code, right? Because you have to execute it. And it has a corresponding entry in GOT, right? This was the GOT on the left here, on the right here, right? So this guy contains an actual offset to the function, right? So normally, but like you essentially say, wow, I know that I have to pick up this entry from GOT and pick up the address. And first time, this address leads you to the resolver. But the second time, it will lead you directly to the function like printf, right? And you start running printf here normally. So you just essentially don't even lose that much time. Like first time you resolve takes a lot of time. It's just, again, why is that I'm talking about this topic? We're never gonna build anything like that. But every time you get a debugger like GDB and start debugging assembly, which might sometimes happen, you will see that, okay, wow, those PLT is there and it takes me somewhere, some weird places, which I don't understand. You single step through assembly instruction, you don't understand what's going on. But by understanding this positional independent code, you will understand that, okay, it's all about PLT and what is going on is resolving. And the second time, you will really jump to the actual function. Okay, let's take a look, right? So each entry in PLT first consists of these parts: a jump to the location which is specified on a corresponding GOT entry, right? So first of all, we prepare the resolver, right? Call the resolver routine, which resides in the first entry of the PLT, and then resolver patches this GOT for the second invocation, now setting it to point to printf. So first time it was pointing back to the resolver, and this is the second time it points to print, right? So after the second, like this is the first invocation, right? So back to the prepare resolver, this jump goes back here, right? And after we did the resolution, instead of jumping back here and then to the resolver, we jump to the actual function, right? Again, kind of like a little bit abstract. So let's take a look at a couple of examples. Again, we have currently my function here, right? And instead of like, since it's not static here, ta-da, without static, the compiler actually doesn't generate the relative jump, right? Instead of like calling this function relatively, it will go through the PLT, right? Because it can be anywhere in the address space. It can be used by other. Okay, so what happens here? So first of all, same as previous, thunk, resolve the address of GOT, right? We first land the current instruction pointer, we save it in the EBX, and then add the offset to EBX in this instruction, right? So this will contain the address of the GOT now, right? Now we push the argument to the function because, well, in the end, even if whether the function was already resolved or yet to be resolved, we still need to pass this argument A, right? So what happens here is that it's EBP plus 8. We save it into EAX, and then, well, in this specific code, instead of doing a push, the compiler already reserved space for this invocation in the stack, and so we're doing a move. Some people might be surprised because I was teaching that it's always a push, but really you can always like compilers are smart. They know, okay, well, I will need an extra 4 bytes on this stack. So let's add 4 more here, right? and just do a move later, right? And at this point you say, well, let's call this PLT. PLT is relative call, right? So it's goes to here. It's actually like minus, it's a negative number because look, this is smaller than this, right? But it lands us, where does it land us? It lands us here, right? So it's this entry in the PLT, right? Which is responsible for resolving a specific function, right? So what do we do here? This is, remember, EBX plus 14 contains address 3A6, right? Because EBX, remember, EBX here contains the actual address of, after we execute this add instruction, contains the address of the GOT, right? So we say, okay, GOT starts at EBX plus some number of entries plus 14, right? And jump to this address, right? So this was the, imagine this was the GOT, right? EBX points here. EBX plus 14 is somewhere here. Let me write it down. EBX plus X14. We'll take this adder, which is here, and jump to it, right? Which address is here? In practice, this address is actually 3A6. So it's exactly the address like in the previous figure. We're returning back here. That's how the linker configured this address, right? Now we have to essentially push some arguments for the resolver. In this case, I guess it's like push that we are like resolving entry number 16 or X10 and jump to the first entry. It's a relative jump. Jump to the resolver, right? Jump somewhere here to the resolver, right? Well, the second time after the address is resolved, right? So again, we did the same. Second time, EBX contained the address of the GOT, right? This is our global offset table. EBX points here. EBX plus 14 points here. And this adder now already contains the address of this myutil function, right? So you will jump directly to this function after that, right? Because that's what resolver did, right? So what did we gain, right? The biggest advantage of position-independent code is that now those libraries, remember this is like code of libc, and then like there's like GOT here, which is like it's part of the data section, right? And there's like PLT here, procedure linker table, which is part of the text section. Like GOT is not shared, but this section code can be shared. It can be located at different addresses, right? Like this and this A is always the same. GOT is different, right? So here it will contain some A, here it will contain some B, here it will contain something else, right? So those are different virtual addresses, right? This is the code. PLT is the same, but like there's nothing to relocate in a PLT, right? And this GOT contains C here, right? GOT, right? And in practice, all this memory, all these three memories, right, of this large code section is backed up by one physical memory, right? It's one physical memory. So only the memory for this GOT is wasted per process. So P1 will have some GOT, P2 will have some GOT, and P3 will have some GOT. But remember, I told you that global data sections are not large. So it's GOT plus, pardon, there will be a data section here, data. GOT is part of the data section, right? And those will not be shared. So because like each of them will have a private instance of data, right? But data sections and GOT are relatively small, and that's important. So you can, those code sections, although I don't write them proportionally, these code sections here, they're big, right? Sharing them is a big plus. So each program has a private GOT. When it's loaded, the linker configures the GOT, configures the GOT to essentially like resolve addresses in the data section. And that's what linker has to do, right? We save some linking time too, because GOT is patched per variable, not per variable instance. a reference, right? Because you might have one global variable in your code, right? And you may be accessing it like hundreds of times from different locations of the code, right? That was your code section, right? And you access it 1, 2, 3, 4, and previously when we were doing relocation, right? Relocation. All these instances had to be patched, right? They had to be changed. But now we change only once in the GOT, right? We say, well, sure, in the GOT, we will change them, but we don't have to change all of that. So it's like it speeds up linking a little bit. What else? So what are the other ideas for advantages and disadvantages of position-independent code? So a little bit of bad, right, disadvantages. So code gets slower, right? You have to, well, first of all, you waste one register, like EBX in our example, to keep the GOT pointer, right? So x86 has 7 registers. If you also maintain EBP stack frames, it leaves you with 6 registers. If you're leaving one of these 6s constantly used to keep GOT, so it leaves you with 5 registers. So that's kind of small, right? On 64-bit machines, it's not much of a pressure though. And we do a couple of more memory dereferences, right? So GOT, instead of like move and do access some memory directly here, right? Which, like maybe CPU can prefetch because it can guess that, okay, I'm accessing it. Now you have to like first go here, access this line, and then go here and access the real variable, right? So it has to prefetch, successfully has to prefetch twice. So sometimes it doesn't matter, sometimes it might matter. So it depends on the, like what kind of programs you run and whether prefetcher is successful or not, right? And of course we do an extra call before, like remember this thunk to figure out the address of GOT, right? This is GOT. So it's one extra call, so it pushes something on a stack, and we save it from the stack and return, right? But the bad, as I said, like a lot of sharing is possible, and plus you can do like the most trivial thing, the most trivial form of address space randomization. It's a basic protection against the attacks. If you don't know where libc is in memory, because when you attack the program, you often need to jump to libc to execute some system call, for example. If you don't know where it is, well, you have to somehow guess whether it's here or here or here. And every time we load a program, libc will be at a different address. It's address space randomization, right? It's kind of not a like bulletproof defense because, well, attackers know there are ways to figure out where libc in memory. Like it's leaked often. You can also do side channel attacks to figure out where it is. So it's not like a complete solution, but still it's a little bit better, right? Okay, and finally, to finish this series of lectures, let's take a look at how we actually load and start programs on real Linux machines. Because right now we went through a zoo of solutions, right? So what we were doing is that we started from C files, we learned how to compile them into object files, right? We can now assemble object files into 2 kinds of libraries, right? So static and dynamic, right? So static libraries are just collection of object files. It's .o, extension .a. Dynamic is largely the same correction, but with some additional tricks, right? Remember, there is some compiler has to know that, okay, we're generating position-independent code. And in our examples, I was always using f no pick because I didn't want to scare you with those thunk instructions, right? But so compiler has to know that, okay, we're talking about, we have to generate POT and, like GOT and stuff like that, right? But right now, you say, well, sure, I got it. There are static libraries, there are dynamic libraries. If you simply build your tiny hello world main program, right, you have a couple of options, right? You say, well, I will generate my obviously main.o file, but then I can, like, imagine I'm trying to print something, right, on the screen. So one thing is to use static and just essentially link against the static libc version, like, right, libc.a, right? and it's fine. So what it will produce a kind of a standalone executable, right? It will be like some file main. The operating system can just simply, essentially, like there will be an entry point, load it in memory, and run, right? Yeah, easy. It will be a little bit larger. However, there's a second option. Instead of doing static linking, and normally you never use static linking in modern programs, like you don't even realize it, right? But typically you don't pass the static flag. What you do is just, sure, it produces a different executable, right? Let me just change the color. Let's make it blue. It's a much smaller executable, tiny main, kind of tiny main, right? Like if in this example, but printf is not here yet, right? It's still undefined, right? And what happens is that the moment you load this program in memory, some magic happens here. We're going to talk about it. So you first load the linker. Linker loads both this main and these shared libraries in here, right? And then patches the GOT of this main program to essentially point correctly to printf, right? So this is loading of a, and during this loading step, here you don't have to do any linking, no linking. No, nothing is needed. Just load and run. Here you load and do dynamic runtime linking because you're still missing some libraries, right? I can give you a couple of examples. Let me show you here. So yeah, so how can we get here? So for example, if we take, if you want to link static executable, like again, no position independent code, for example, our wonderful hello relog from previous example. So, well, sure, you linked it, it produced the out file. And if you do LDD, which shows, okay, dependencies like on out, well, not a dynamic executable, it's ready to run. So if you do opt dump minus disassemble show all symbols, relocation symbols, LE, well, the entry point is here, but essentially it's ready to go. Okay, let me show you the entry point. Read elf will show us the entry point of this out file. Its entry point address is 8048. So it's relocatable file. So I think you can move the file and relink it to run at a different address. But by default, the operating system will start it at this address, right? So to save probably this relocation. So when you start from the, this is your enter point. Like it's not at the very beginning of the file, right? So it's start, right? And what will be happening at some point, well, it will start this libc start main. We'll talk a little bit about it. And eventually libc start main will start your main, right? And the printf, like if you, for example, say, do I have it undefined? No, everything will be, printf will be here as well. So if you want to search for printf, you can find it, right? So like, let's do this. Like, let's search for printf here. Where is it? IO printf. Yeah, so this is like various, your main essentially. If you search for a main, do we have it somewhere? Like somewhere, the beginning of a file. Oh, again. I lost it again. Let's search again. That's your main program, right? So when you call printf, it's actually in your address space. So this is specific address, right? So it's a relative address from this, right? And this is where this, where this IO printf is located. It's called from multiple places, but here it is, right? And if you do something different, like if you say, wow, what if I remove this static thing? Now your LDD will show you that, by the way, you depend on libc. This is the linker itself, which has to link the program, right? So, and if you still do something like read elf and grab for undefined symbols, well, you see that printf is still unresolved, right? Okay, so how do we start statically linked programs, the ones which are ready to run? The only magic which I want to emphasize again in this lecture is that main is not the first function which gets to run. So why is that? Well, first of all, like, let's a little bit of a background, right? Let's change the color back to red. Well, it works as you might expect. Remember our OS interfaces. So someone calls exec-v, like exec, one from the family of exec system calls, right? And what happens is the kernel reads the program from disk, right? And well, the kernel itself, Linux kernel, can handle multiple executable formats, right? So, and it has handlers for each of them, right? It tries all of these handlers until one of them succeeds, right? So, for example, remember, you can say, wow, by the way, I have this executable bash script, right? So which says like something like bin.sh, right? Well, it's not even an elf file. It's a text file, which I really like try to run with maybe like even exec, right? It's fine. So the kernel will have a handler which will look for these characters, right? And then understand that it's a script, and it will have a script, and then it will start the interpreter for this script, something like bin.sh, like same for maybe Python if you like. And then like execute this bin.sh with this input, right? But we will concentrate on elf, right? So at some point, one of these handlers, which is an elf handler, says, okay, I got it. It's this blob which we read from file has an elf header, right? So it's okay. I can load it in memory, right? And normally, well, the goal is to get to main, but main is a little bit tricky because there is a notion of constructors and destructors. And you might say, okay, well, am I executing like C++ program? Well, no, the constructors and destructors were invented even before C++. So some libraries might need to open a file, for example, before even main is running, because maybe main using some IO like tracing function. And this tracing function traces everything in a file. So, well, this file has to be opened, right? So that's why, well, before running main, we'll descend here and we'll execute all these constructors right here. And then we'll go back and execute main, and then we'll execute, well, destructors as well, because, well, you have to close this file. And so a couple of things here. So if you want to see the backtrace, like normally when you start a program and you backtrace saying, okay, what was running before me, you will only see up until main. But if you want to see the backtrace past main, use this command, right? And then if you do something like backtrace, you will see that, okay, well, actually, yeah, the execution really started from start label. Then it invoked this libc start main, and then I got control to my main and my program was running. So that's not a joke. Like, I'm not kidding. Like, your program was really loaded this way. And alternatively, if you want to see what happens before main is running, right, set a breakpoint to the start label, meaning that, for example, you can either do like breakpoint start, or you can do this, figure out this entry point address and essentially set a breakpoint at this address. Sometimes it's useful. And essentially, my idea is that like, wow, languages like C++ need constructors and destructors, but I was saying that even some C libraries might want to have the same program, right? So what happens is that the startup code in every module is put into an anonymous startup routine, right? And it put in this segment called init, right? And well, order matters, and it's kind of hell because, like some constructors might depend on execution of other constructors. And ideally, you should like really build this like kind of a dependency chain, right, between them. But this is not done, so no one does it. So we only like figure out two layers. So system libraries go first, and they go in this init section, and then user constructors are in the CTOR section, right? So it's some kind of a compromise. So system constructors run first, and then user constructors. If you want to like take a look at how it's done, so for example, this is what you can do in your C program. So you can see like in GCC attribute constructor, here it prints the name of a function, and then your main, if you run it, you will first get a constructor here, like name of this function, some printf from here, and then you get a printf from main. So the constructor did really run before main. Yeah, so okay, it's fine, but that was for the statically linked program. Remember now, dynamically linked programs. dynamically linked programs are not ready to run yet, right? Because you have this tiny, tiny main. Remember, tiny, tiny main asks for printf because it calls printf, but this printf is nowhere around. So what needs to happen? What do you think has to happen? A little bit of trickery happens. So first, the kernel maps elf sections into memory. It will try to run those handlers, right? But it looks for whether the interpreter section is present. It means that an interpreter should run first. And this interpreter, typically it's called something like LDSO or LD Linux SO. It's a linker. It's a linker which has to run before the program is ready to run. Because, okay, a linker, what it will do, it will take this main, it will figure out that it needs like libcso library. It will go to file system, read this libcso library into memory, right? It will do will patch the GOT of the main, right? Making sure that it points here. It will relocate libcso as well. So it will patch GOT of libcso as well to point to the data section correctly, right? And then at some point it says, okay, you're ready to run, it will jump to main, right? But this loading has to be done. And maybe libcso, maybe the program itself, like libcso depends on some other libraries, like, I don't know, something foobar. Well, these libraries also have to be loaded recursively. So before the program runs, this linker is running, right? So what happens here is that the kernel itself understands that this is the program which has to be linked first. It loads this library, LDSO or LD-Linux-SO into memory. And instead of starting the program itself, it starts this library, right? The linker first initializes itself because, well, it doesn't really know at which address it is loaded, right? So it can be different. So it has a tiny bootstrap section which relocates itself quickly, right? It's kind of funny. Linker relocates itself. And then it starts loading the shared libraries required for running this program, right? So, and there are some information in the file for like which libraries have to be loaded, right? So, okay, this is like yet another like slide on the same topic, right? The kernel itself checks for whether the interpreter section is present. It reads the file name of the interpreter. It can be different, right? In our example, it's like LD Linux. So it finds it, loads it in memory, right? It has to be elf executable, by the way. And it starts the entry point of the program to start running the ld.linux. And at this point, execv returns, right? It's just the first process which did, wow, it's the same process, right? At this process, execv returns and it starts running ld Linux here, right? Because it's got loaded in this address space. Remember, exec reloads the address space of the program with the new program. So how do we find libraries? Well, there are some well-defined locations. First of all, you can use the rpos symbol. It can be linked into a file by a normal linker at link time. You can say, well, library poses such and such. You can also use this file, which is etc/ldso-conf, and that's the most common way, right? And then you can default to like default library path, right? But essentially, the linker knows where to find libraries. It will be searching for them, and there is a specific algorithm for the ordering of those paths, and you can actually replace the library. It's called like LD preload, right? And when the library is loaded, well, the linker descends recursively, right? It has to like understand that maybe it depends on other libraries, and it will load them as well. So this is a little bit tricky, but in the end, you kind of got it. So it works. So every time you typically start a tiny main program, instead of main first, LD runs, LD loads other libraries, like at least libc, right? Do all the like GOT patching here and here, And after that, you're ready to run. Of course, the same hierarchy of constructors will get executed as well, right? So like the linker itself does not directly jump to main, but it will descend into this executing constructors, then main, and then kind of like finalizers later, right? So, and I was like kind of glancing over it, but what do we need to do, right? Well, position independent code needs relocation in the data segment, right? So essentially what it happens is that you patch the GOT, right? So like linker does this GOT patching. Okay, so finally conclusion. So that's kind of the end of this 2 lectures on linking and loading. So what happened is that first we learned calling conventions. We know how to essentially call functions, how to like essentially push arguments on a stack, do a call instruction, how to maintain the stack frame, right? Then we said, okay, so got it. So we understand how simple assembly code or machine code looks inside, right? How do we assemble real programs? We started looking at linking and then did relocation, which allows us to essentially move the program statically in the error space, right? So essentially move it. It was linked, for example, to run at 0, but well, we want to run it at some other address, right? So we relocate. Or when we merge multiple object files together, right? We have to merge them together, and that triggers relocation to begin with. And now finally we understand how position independent code and dynamic libraries work, right? Static and dynamic libraries. So more or less, you kind of know everything about what's inside the process. We don't know much about virtual to physical memory, and that's essentially the topic of our next lectures. Like we will look at the address translation mechanism, but more or less we know how the programs are running, what's inside them, right? And at this point, we're kind of ready to like start building the yellow part, the kernel, right? So if we understand virtual to physical, we kind of already know what's inside this part, right? This is the program. What we need to do is just from the moment we power on the CPU, we need to boot into this kernel. And after that, we'll be building this kernel and we'll start implementing something like exec, right? Well, it's not that hard. So it's a lot of interesting fun coming. Okay,